Hey, good morning, everybody. This is Mr. Ainsworth again, and we're going to get into lesson 6 here in pre-calculus. And let's go for it, okay? We're going to be discussing horizontal and vertical asymptotes, holes, limits to infinity to find those asymptotes, and where the function's undefined, a lot of things, okay? So let's get started. We got this rational function up top here, g of x, and the graph is given off to the right. And what we want to do is complete the table. We want to be able to find the horizontal asymptotes by looking at the degrees of the function from the previous lesson here. Find intercepts, figure out where it's undefined, all kinds of stuff. All right, so here we go. The first thing what we're going to do is we're going to simplify first. So let's write that out first. Always when you're dealing with rational functions, you always want to simplify the function. So first, and notice there's a common factor of x minus 3, and x minus 3 divided by x minus 3 here is equal to 1. And so let's write the function. So the simplified function, that is, so g of x here is going to be equal to x plus 5 divided by x plus 1. That's the first thing. Okay. Now notice in the very beginning, I'm going to skip to number 3 here and just talk about the original function here, g of x. It says for what x, values of x is g not defined. Okay, this tells you about the domain. So let's go down here. We want to figure out what the domain is. It's all reals except where it's undefined. Okay, so the domain here, let's talk about this, is all reals. You can substitute any real number in there. So all reals except where it's undefined. So except what? Except for, let's figure this out. Let's go to the function here. We know that we cannot divide by 0. So when you look at the function here, you got to figure out what values make the denominator equal to 0 and exclude that from the function, because this, you can never divide by 0. In fact, let me write that out. So you cannot, okay, divide by 0. You never could, and you never will be able to. So here, looking at this factor here, the x minus 3, x can't be equal to 3, okay? Looking at the x plus 1, x cannot be equal to negative 1, all right? So right there, that is what you look at when you figure out the domain. So the domain is all reals, okay, except 3 and negative 1. So all reals except 3 and a negative 1. The way you write that is x is not equal to 3 and negative 1. That's how you write it. Okay, so where is it not defined? Well, 3 and negative 1. So actually, I just wrote that down up top, so I'm just going to say the answer here. So what values is it not defined? Well, g is not defined. Is not defined at x equals 3 and negative 1, because you cannot divide by 0. You cannot divide by 0. Okay, it's undefined. Okay, so we answered number 3 here, and we simplified the function. And let me see, part A, it says find the limit of g. Okay, so let's do that. So the limit of g. So the limit of g as x approaches infinity. So the limit as x approaches infinity of my function. Now use the simplified function. Okay, x plus 5 divided by x plus 1. And notice that the degrees are the same. All right, so you look at your dominant terms and look at the degrees. The degree up top is 1, the degree down below is 1. All right, and you look at the coefficients right through here. And from our last lesson, we noticed that if the degrees are the same, in fact, let's write that out. The degrees are equal, which they are, they're both first degree. You take the coefficients, which are 1 and 1, divide them, and you get 1. And that tells us that we have a horizontal asymptote at y equals 1. So let's draw it in. You can see the function right here has a horizontal asymptote at y equals 1. That should make sense. Now, you really can't really see the asymptotic behavior unless you go to Desmos and go out to infinity. So when you do that, we're going to see it a lot better. Okay, in fact, let me bring in Desmos right now so you can see it. Okay, so when you when you take a look at the function, and notice that I already have it graphed up here on the decimals on the right, if you squeeze the x-axis here, let's see if I can do this. There you go, and you go further out to infinity here as x increases from 20 to 40. All right, squeeze the x-axis here. You can see how the function approaches that green line there at 1. Okay, that's y equals 1. And right now we're already at 100. So when you look at limits to infinity, you want to go far to the right or far to the left, like to 100 or 1,000 and 10,000 and go way beyond. So right now I'm at almost 300 here. You can see how the line approaches that. I mean, the curve approaches the horizontal line. So looking at horizontal asymptotes and evaluating limits to infinity, you want to go far to the right. So you can see that. Okay, so we have a limit, a horizontal asymptote at 1 because we had a limit there. It's equal to 1. And again, that's using techniques from the previous lesson here. And now what we're going to do is evaluate the table. So let's go for it. So we have, so at -5. So -5, you substitute it in. So g of -5. And again, I'm using the simplified function here. I'm using x plus 5 divided by x plus 1 here. This is your simplified function here. You substitute -5 in there, you get 0 divided by -4, which is obviously 0. And then you substitute -1 in there, you get -1 plus 5 divided by -1 plus 1. That's 4 divided by 0. That's undefined. If I can spell it. Come on, Ainsworth. I've already produced many videos this morning, so undefined. What does that mean? Well, at x equals -1 here, at x equals -1, it's undefined. And look at the graph up here. You have a vertical asymptote. So grab another red pen, or let's switch colors actually. All right, and then draw your horizontal or your vertical asymptote at x equals -1. It's called a vertical asymptote at x equals -1. And so when the function is undefined at a point like this in a simplified function, that indicates you have a vertical asymptote. Okay, that is called a non-removable discontinuity, just so you know. Non-removable discontinuity. Okay, a vertical asymptote. And why is it called non-removable? Well, it's because we couldn't simplify it anymore. If you look at the simplified function, let me highlight it here. Your simplified function right there. It has a non-removable discontinuity at -1 because you cannot, or the function's not defined at -1. So x is not equal to -1 there. And you can't simplify it anymore, so it's non-removable. Before, we had a removable discontinuity at 3. Okay, so at 3, that became a removable discontinuity because we simplified the function there. So at x equals 3, we have a hole. Look at this. On the graph, the hole is located at 3, 2. Now, how do you know it's 3, 2? Well, you substitute in the function, right? So at 3, if you substitute in 3, you get 3 plus 5 divided by 3 plus 1. That's 8 divided by 4, or 2, and you see a hole there. That right there is called a removable discontinuity. We canceled out the common factors of the numerator and denominator, okay? And because we canceled it out, we removed it. We removed the discontinuity by simplifying it, right? We removed it, canceled it out. Removable. It's still a discontinuity. It's a hole. It's not, the function's not defined there, okay? So we removed it, we simplified it, and we found it by substituting 3 into the simplified function. We got 3, 2. All right, so that is your hole. We have vertical asymptote at -1. We have a horizontal asymptote at y equals 1. We have a hole at 3, 2. Let me see, we have a y-intercept here. Let's substitute 0 in. So 0 plus 5 divided by 0 plus 1. That's 5 divided by 1, or 5. You can see that. Go to the graph here. You can see this right here. It's called a y-intercept, okay, at 0, 5. And then we have an x-intercept at -5, 0. That's called an x-intercept. How do we find that? Well, you set the function equal to 0, okay? And when you set the function equal to 0, let me do it somewhere here. So we have x plus 5 divided by x plus 1. When is that equal to 0? Well, it's when the numerator equals 0. And so if you take x plus 5 and set equal to 0, you're going to get x equals -5. And that, my friends, is the x-intercept. So a fraction is equal to 0 when the numerator equals 0. It's a key concept, and that's how you find an x-intercept. So I'm going over all the learning targets right now. Okay, to find an x-intercept, you set the numerator equal to 0. To figure out where the function is undefined, okay, you want to look at where the denominators equal to 0. So denominator, when is that equal to 0? Well, it's when x minus 3 is 0, which means at 3. And then it's also when x plus 1 is equal to 0, so it's at -1. And again, so when you're looking at where it's undefined, you look at the denominator. When you're looking at where the find the x-intercept, you want to look at where the numerator is equal to 0, so you can figure out the key features. Okay. And then last one in the table there, when evaluating the function at 4, so it'd be 4 plus 5 divided by 4 plus 1. That's 9 divided by 5, 9/5, or 1.8. Okay, there we go. Now it asks you some questions here. So let me bring in the graph again. Let me see here. Bring in Desmos. You guys got to get used to this here. So look at this cool technology here. Got Desmos here. Let me plot the hole so you can actually show where the hole is right there. Look at that. Isn't that cool? And so I'm going to screenshot that and bring it into my lesson so I can take a look at it here. All right, so I'm going to resize it. When you do this, you got to look at your iPad and figure out what buttons to press to screenshot. It's a pretty cool feature of the iPad here. Click check marks, copy and delete, and then just press on text mode, press and hold on your iPad and paste it in. Look at this. All right, this is pretty bitchin'. Okay, so there you go. By the way, you can say that. That's an 80s word. That means totally rad. Whereas you guys say in today's world, that's sick, man. Okay. All right, so we got this cool graph here, this rational function that I have on the right-hand side, and they ask you, describe what happens at -1. Well, we talked about that, right? So at -1, let me make this a little bit bigger here so we can see it better. Okay. So at -1, so at -1, this -1's right here. Ah, come on, let me grab a pen here. So at -1, we have a vertical asymptote, as I was talking about, at x equals -1. And then, so what's happening there? Well, we have a vertical asymptote. Why does it happen? Well, because we have a non-removable discontinuity. So let's write that out. So, okay, at x equals -1, there is a vertical asymptote, right? Because the function is not defined there and it's non-removable. Remember, the simplified function g of x is x plus 5 divided by x plus 1. It's not defined at 1, or -1, excuse me. So there's a vertical asymptote at x equals -1 because there is a non-removable discontinuity, as I said it earlier. So because there is a non-removable discontinuity, the function's not defined there. Discontinuity, okay, the function's not defined at -1. You can't divide by 0, okay? G of x is undefined, okay, at x equals -1. So I repeated what I said a few times, so hopefully you understand what's going on there. And then what happens is you get closer to -1 from the left, all right? From the left, and then what happens when you approach -1 from the right? These are called left and right hand limits. Okay, so let's write it out first. So as x approaches -1 from the left, so you use a little minus sign, all right? what's y approaching? And then as x approaches -1 from the right, so we use the plus sign, what's y approaching? Well, let's look at the graph, right? So here we go. So here's your target point. So get your eyes right here on the vertical asymptote. That's your target point. And if you approach -1 from the left-hand side, okay, whoa, let me grab my red pen here. If you approach your target point from the left, again, this is the left side, and over here is the right side. Okay, if you approach it from the left, notice the function is decreasing without bound. Okay, it's going down, it's going to -infinity. It's decreasing without bound as you approach it on the left-hand side. So we say as x approaches -1 from the left, the function g approaches -infinity. Okay, so -infinity here from the left, and then you write that as a limit. So the limit of the function g, right, as you approach -1 from the left, so use that little minus sign, all right, is equal to -infinity because it's going down. Now on the right side, what's going on? So let's go back to the graph. Now, if you're getting closer to the vertical asymptote from the right, so here's the right side. Now look at blue. You're coming in from the right. The function is not going down; it's going up. Okay, it's increasing without bound, increasing without bound. And what that means is that you're going to positive infinity because it's going up without bound. So coming into the right side of the vertical asymptote, the function goes up. Okay, so how do you write that? Well, first of all, y approaches positive infinity. And then when you write it, you say the limit here as x approaches -1 from the right-hand side. So use the plus sign. So plus sign for the right, minus sign for the left. Okay, of the function g of x is equal to positive infinity because the function is going up. Okay, and remember this arrow means approaches. That's what the arrow sign means, or the arrow symbol. So as going back to number 5 now, as x approaches -1 from the left, y goes down without bound, decreases without bound, so y approaches -infinity. And then from the right, if you approach -1 from the right, and again, this is a vertical asymptote here, so these two deal with vertical asymptotes, you have a limit to infinity from the right because it goes up. Now here, you're dealing with the hole, okay? So what happens at the hole? Okay, so we have a hole, okay, at x equals 3. In fact, it's located at 3, 2. We talked about that earlier in the graph. Okay, we saw it in the graph. We also talked about that it's a removable discontinuity because in the beginning we canceled out the x minus 3's, those common factors there, and whenever you cancel out a common factor, you have a hole, and then you have to find the location of it. Okay, but what is the behavior when you approach the hole from the left, and what's the end behavior when you approach it from the right? What's going on with the y values of g? Well, let's go figure that out. So let's go to the graph again. Now get your eyes on the hole here. Okay, so right here, let's find 3 on the x-axis. It's not labeled. So now your target point is 3. I refer to that as the target point. Okay, just like -1 was the target point earlier, now get your eyes on 3. Now let's come in from the left-hand side. So you're approaching 3 from the left. Okay, this is the left. Okay, over here is the right. Make sure you know the left and the right. Okay, so when you're coming in from the left of 3, now the function is decreasing, and as you get closer to the hole, these y values get closer to, guess what? 2. All right, that's the limit because it hole's located at 3, 2. So as x approaches 3 from the left-hand side, y is approaching 2. Okay, now on the right, as x approaches 3 from the right-hand side, so you put a plus sign up there, the function now, if you're getting closer and closer to the hole, the y values are getting bigger, they're increasing, and they're getting closer and closer to 2 because that's where the hole is located. So the y values are approaching 2. And this is the behavior of what happens when a function approaches a hole. It actually approaches a unique y value, and this value is called the limit. Okay, now let's rephrase that down here. Okay, so here we go. So as I just said here, as x approaches 3 from the left, use a minus sign. Y approaches 2, the limit. The y value. It's a y value. Okay, and then you write that. Write that as a limit now. So you say, so the see, so you write it as, let's see, I'll write it right here. The limit as x approaches 3 from the left of your function g of x is equal to 2. That's how you write it. On the right hand side, you say as x approaches 3 from the right, y approaches 2 again, it's the limit. And then as you write it here, you write it in limit notation, which means the same thing. As you approach 3 from the right, using the plus sign, of your function g, you have to write that function in there, that is equal to a 2. Okay, it's the y value, it's called the limit. Okay, and then again, when you look at an intense lesson like this, you have to slow down, go at your own speed. And since it's a video here, guys, you should be pause, play, rewind, listen to it again until you fully understand it. Especially if you're taking notes for the first time. If you're at home and you missed the day in class and you're going through this with me virtually here, after you take notes, listen to it again without taking notes, and then see if you fully understand what's going on. Okay? And then try your homework. Don't try to attempt your homework without understanding all of this, because this left and right hand limit stuff is new. You didn't discuss that last year. Okay? So number 5 is called a left hand limit. Left hand limit, because we're coming in from the left, and this is called a right hand limit because you're coming in from the right. And again, you're going to be using all of this next year in calculus. Your first unit, you're going to be discussing limits because they're related to what's called a derivative, and you're going to learn how to differentiate a function, which is going to how you're going to get your instantaneous rate of change that we've been talking about this semester here. Okay, in pre-calc. It's going to be pretty neat where you're going to put all these ideas together. All right, and then, so let's do this. Let's summarize everything here, what I said, and then apply it to another one. And then we can apply it. Okay, so here we go. Let's write down and summarize what I've stated. So LT is learning target. So the first learning target. Okay. First of all, given a rational function, okay, always, and put this in red, always factor first. Always factor first. As you can tell in our check for understanding here, look at it. This is in standard form, and what we're going to have to do right there here is we're going to have to factor, okay? We're going to have to factor the polynomial before we find the zeros in the y-intercept or anything. So if they don't factor it for you, well, guess what? You're going to have to factor. Okay, that's the first one. Second one, learning target number 2. All right, so what did we do? So we talked about x-intercepts. Okay, so when finding x-intercepts, okay, which are called zeros, what do? So let's go back to the lesson here. What did we do here? So learn from the example. So when we found, look at number 2 now. When we found the x-intercept, it's where the numerator is equal to 0. So just set it equal to 0 and solve for it. You get your x-intercept. Okay, let's write that down. So here, set numerator equal to 0 and solve. Okay, next learning target, number 3. Okay, let's talk about vertical asymptotes. Okay, vertical asymptotes. Okay, what do we do? Well, let's go back up there and let's see what we did, right? So you learn from experience. So what we need to do is we simplify the function, like what we did here. All right, we simplified, we cancel out the common factors of x minus 3. We got a new function, or a simplified function. It's the same one, just simplified. And we got x plus 5 divided by x plus 1. And we looked at the denominator, and we asked ourselves, what makes the denominator, equal to 0? All right, when is x plus 1 equal to 0? So to find your vertical asymptotes here, we set the denominator equal to 0, and we solve. Okay, so let's write that out. So here, when you find vertical asymptotes, you set the denominator equal to 0 and solve. All right, and usually it's pretty easy when it's in factor form. You can do it in your head. All right, the next one here, learning target number 4, horizontal asymptotes. Okay, what do we do? Well, we take limits to infinity. Okay, let's see what we did in part A here. Look at that. We found the limit of g of x. And you kick in all your degree rules. You look at degrees. All right, and so we take limits to infinity. So we have to find or evaluate the limit to infinity. So find the limit as x approaches infinity of the function and see if you get a number here. Okay, and if it's equal to a constant, when I say constant, I'm talking about a real number. Okay, real number. I don't care whether it's positive, negative, or 0. Positive, negative, 0. And you don't get infinity, then you have a horizontal asymptote. And the horizontal asymptote, in general, is y equals whatever that constant is. Okay, so whatever you get here, that's the horizontal asymptote. Okay, so like in what we did, let's go back to the beginning just so you understand. We got a limit of 1, so the horizontal asymptote is at y equals 1. It's that simple. Okay, and if you don't get a constant, you get infinity, it doesn't have a horizontal asymptote. Okay, and the last one here, learning target number 5. Okay, let's talk about holes here. So if it has a hole, then it has to have a removable discontinuity. So if a function has a hole, in fact, let's write that like it. A function has a hole if you can find a removable discontinuity. If you can remove the discontinuity. Now I'm saying this in a new fashion, so let me make sense of it to you. Okay, so if you can remove it, okay, what do I mean? Cancel out a common binomial. Cancel out the common binomial or factor. So what do I mean by that? If we go back to the beginning here, we saw that the function has x minus 3 in common in both the numerator and denominator. We cancel that out, and that indicates that you have a hole, okay, at x equals 3. And we saw that, let me see, in here. So we had a hole here, this one. Okay, and it was located at 3, 2. And we call that a removable discontinuity because you removed the factor to simplify it. You removed it by canceling or by simplifying. Okay, and that's it. So now all we have to do is go ahead and apply it and see what happens. So let's apply it here and let's finish up. So the first thing you do is you factor. So here we go. So f of x now is going to be, let me see, x squared minus 4. That's called a difference of squares. So difference of squares. This is an algebra 1 thing that you started learning a long time ago. Okay, and a squared minus b squared, that's equal to a plus b times a minus b. Okay, so this one here is let me keep it in red here, is x plus 4 times x minus 4. And then here on this one, the trinomial here, do you guys know of two numbers that multiply to negative 4 and add to a 3? Hmm. How about negative, let me see, positive 4 and negative 1? 4 times negative 1 is negative 4, and 4 plus negative 1 is 3. Okay, so here we go. So we can factor this as x plus 4 times x minus 1. You could check that by multiplying it and using FOIL. Okay, now notice we have a common factor here. We have a common factor here, and if you simplify them right here, we have a whole. Okay, so we just used one of the learning targets, right? We have a whole if we can remove the discontinuity. So I'm going to remove it here. So right here, I have a whole at x equals negative 4, wherever makes it 0. So here we have, it's going to be at x equals negative 4, but we need to find the location of it. So 4 comma something, you know. And so I'm going to rewrite the simplified version of the function. So my simplified function is now x minus 4 divided by x minus 1. So here, if I find g of negative 4 using my simplified function, so I get negative 4 minus 4 divided by negative 4 minus 1. That's negative 8 divided by negative 5. That's 8/5 or 1.6. Okay, so now I know where the hole is located. Now zeros, this is where the numerator is equal to 0. Go back up to the very top. When finding zeros, just set the numerator equal to 0 and solve. Okay, so here we go. I'm going to take x minus 4, so x minus 4 equals 0. So I have an x-intercept at 4. It's exactly at 4 comma 0. And then y-intercept, you set x equal to 0 and solve. So you evaluate the function. So f of 0, what is that? Well, what's 0 minus 4 divided by 0 minus 1? And that's got to be 4. So I have a y-intercept at 0 comma 4. Equation in the vertical axis, asymptote, excuse me. Okay, you want to set the denominator equal to 0. All right. And so that right there, when is x minus 1 equals 0? Well, it's at 1. So we have a vertical asymptote at x equals 1. And then, are there any asymptotes? Well, that's a limit to infinity. So we take a limit of the function of the simplified one now. So I'm talking about this one. So let's bring it down in here. So we're going to take the limit of x minus 4 divided by x minus 1. And then what do we have? Well, the degrees are the same. So notice, look at degrees. Look at degrees. And this comes from the previous lesson right through here. They're both first degree. They're the same degrees. Same degrees. And if the degrees are the same, you take their coefficients and divide them. And the coefficients of the dominant terms are 1, both 1. And 1 divided by 1 is usually 1, which tells me that we have a horizontal asymptote at y equals 1. And when we graph this, we're going to see it. Okay, so let's go ahead and let's graph this function now. Let's bring in Desmos again. And again, you need to be able to do this on your iPad at any time. So you got to get good at using the technology here. So I'm going to turn off the previous function. Do not delete them, okay? Save your work, as I just did. And then type in your new function, which I already have it typed in. And so here we have this function, and we have a horizontal asymptote at y equals 1, so I'm going to select that. We have a vertical asymptote at, where to go, x equals 1. So let me type that in here. Oh, here we go. And let's see here. There we go. So x, there we go. I want to change the colors. You want the asymptotes to be dotted. And so let's make both dotted here. There you go. So we have these imaginary lines, these vertical and horizontal asymptotes that are dotted, the green and red ones here. Notice as the function approaches those, whether you go up or down, left or right, they approach the vertical asymptotes and the horizontal asymptotes. Okay, and let's see. So everything that I said is there. Now we have a hole at -4 comma 1.6. Now Desmos does not or cannot show you where the hole is because it's not defined there. So it's not that sophisticated. So go down here, type in the hole. So parentheses, okay, -4, just type it in, comma, and then 1.6. All right, and then let's make a label for it. Let's say hole. So just type it in, and then at -4, comma, 1.6. And then what you do, watch this, click on the gear, and then click on your hole here and make it look like a hole. There we go. So pretty cool. Use Desmos effectively here. Look at that. And you can see the function, the table, the asymptotes, and the hole. All right, click save your work. And I'm going to screenshot this and bring it in. Again, this is just iPad stuff that you can do to record your work and make sense of it. Okay, so click checkbox, copy and delete, and go to the side of your document, press text mode, the T, press and hold on your iPad, and then paste your graph in here, and now you have a cool record of, of your graph. Here's the function right there. Pretty cool. Okay, so now we have the graph on the right. You can sketch it here. Number 3, they ask you for the sketch. And when you do that by hand, as opposed to Desmos here, you always start off with the asymptotes first. So what you do is you just sketch it here. So at x equals 1, plot 1, and you draw a vertical asymptote at x equals 1. Then you draw the horizontal asymptote at 1. So y equals 1. This is what you do if you're just sketching without a graphing aid like Desmos. And then you plot the hole. The hole is at -4 comma 1.6. So 1, 2, 3, 4. That's -4. 1.6 is up here. And then the y-intercept is at 0, 4, 2, 3, 4. So it's here at 4. And then an x-intercept. Where's the x-intercept? Where'd it go? At 4. And then we have 4. So 1, 2, 3, 4. So at 4 here. Okay. And so if we're going to sketch this bad boy, okay, we know it's asymptotic and it's got to go through the y-axis right there. And it's got to hit the hole and it's got to continue this way. And then here it's got to be asymptotic down and asymptotic to the right. So when you sketch functions using the behavior, you understand what it means to be an asymptote. You plot the x and y intercepts, you plot the hole, and then you sketch the function. And it should match what you came up with in Desmos. Okay. Also, last thing here, number 2, this is kind of a cool thing here. Estimate an x value or evaluate the function at x value to the left and to the right of the vertical asymptote to determine whether it's going to either infinity up or -infinity down. And the way you do that is you pick a close number to the vertical asymptote. Now remember, our vertical asymptote is at x equals 1. So we need to pick a number very close to 1 on the left. So left side, left, sorry. So let me start over. So left of 1. So how about, let's evaluate the function at 0.0, how about 9? Let's get really close, 0.999. And on the right side, let's get really, really close. Okay, and what's a point to the right of 1 that's extremely close to 1? Well, how about 1.0001? Now the way you do that, so let me bring up Desmos again. The way you do that is simply by entering your function in. So again, you got to type your function in, and then I'm going to redo it for you guys. So let me delete this here. And then I'm going to click on the gear. You go to your function, you turn it to a table, select table, and then you pick values that you want to evaluate the function at, such as 0.999. So just put a bunch of nines in there, and look at that. You get 300,001. So if on the left side, you get an extremely large value, which means it's going up. And then on the right side, that's 1.00001. Well, let's take out some zeros so we can see it, okay? And look at that, you get almost negative 300,000. So that tells you that if on the right side, the function is going down to negative infinity. On the left side, 0.9999 is very close to 1, all right? And you get this huge y value, so it's going way, way up, okay? So this is telling me that on the left side here, so let's annotate a little bit. This is on the left side, all right? It's going up to positive infinity. It's going up. It's getting huge. And on the right side, okay, right, this is on the right side of 1 because it's a little bigger than 1. You're going down, okay? This is extremely small, so it's going down to negative infinity. And that suggests the limits, okay? So this is about, again, this is 300,000 or 30,000 actually. No, actually I put another 9 in there. So 300,001. And then this one here is negative 299,999. So when this suggests now that the limit of the function as x approaches 1 from the left, okay? So if you're coming in from the left-hand side, you get infinity because it's going up. And then if you take the limit of the function as x approaches 1 from the right-hand side, so use that little plus sign, all right? If you're going from the right, it goes down, so it goes to negative infinity because the function is going down. So these are called left and right-hand limits. Left and right-hand limits. What's happening from the left? And again, our target point is 1 here. There's our target point. And if you approach the function from the left, the function goes up to infinity. If you're coming in from the right, the function is going down to negative infinity. And that, my friends, is what you have to get used to. This is a very technical lesson, and it involves a lot, and it's a very important one, especially for those of you guys who go into calculus, because you're going to start off the first few weeks in your first unit talking about limits, okay, and its relationship to later on what's called derivatives, okay? Hopefully that helps you out. And again, when you're watching a video like this, you go at your own speed. You should be pausing, playing, rewinding until you fully understand it. And it might take a couple times. So do your best, and hopefully I'll see you in class. Take care.